This is 7.2. And hopefully you've already watched the video for 7.1 because we're going to build on that in this 7.2 video. So regular Markov chains is what we're looking at here. Bad underline, but that's okay. Let's do that better. Regular Markov chains. All right, so we're going to start off with 3 quick definitions. First, let's just recall what a Markov chain is. So I'll give you the formal definition and then we'll do the intuitive definition. So you could say a Markov chain is a sequence of trials. There we go. So sequence of trials where the probability of moving between states is given by P. Okay, so that's our definition there. Let's just clean up the handwriting. Put my tablet in a slightly better position so that I can write in a straight line. Okay, so there we go, moving between states is given by P. Great. So when we say sequence of trials, we mean something like, for example, sequence of shampoo purchases. That's what we were talking about in 7.1. So imagine these consumers are going out and buying shampoo, say once a month. They're doing that month over month. And we were talking about whether those people would purchase our brand of shampoo or a competitor's. So when we say the probability of moving between states is given by P, well, the states would be, in that example, yes and no, meaning whether the consumers were buying our brand or not. And when we say given by P, P is just a fancy name for the transition matrix. Or rather, it's notation, quick notation for our transition matrix. P is the matrix that encodes how likely it is that consumers will stick with our brand or switch to a different brand, for example. So that's what a Markov chain is. We talked all about that in 7.1. So we got 2 more definitions to go here to start to talk about this word regular that appears in the title. So let's say that a transition matrix is regular if some power of P has only positive entries. Okay, and I think this might be a little bit more precise if we say a transition matrix P is regular if some power of P has only positive entries. So we'll do an example in just a second and see what that looks like. And then from there, we can talk about what a regular Markov chain is. So think of a Markov chain as a sequence of shampoo purchases, for example, or a sequence of stock prices day over day. That was another example we saw in 7.1. You could say that you've got a regular Markov chain if the transition matrix P is regular. Well, I don't really need to say if. I'll just say I'll define a regular Markov chain to be one where P is regular. So let's jump into an example. We'll get used to these definitions here. So Markov chain, we already covered that in our previous section, but the 2 new definitions here are really what it means for a transition matrix to be regular. We'll practice that, and what it means for a Markov chain to be regular, which is just saying the transition matrix that encodes the transition should be regular. All right, so here's our example. Question is the Markov chain regular? And we're going to do 3 parts here. So part A, B, C. All right, let's say for part A, P is the matrix 0.3, 0.7, 0.9, 0.1. So let's go back to, and we're asking the question, is the Markov chain regular? Okay, so what it means for a Markov chain to be regular, P must be regular. What that means, this is our main definition here, we need P or some power of P to have only positive entries. So you're basically just looking at this matrix and making sure that there are no zeros in there. So we can say, yes, all entries are positive. There are no zeros in that matrix, so the answer is yes. All right, let's try part B. Let's say P looks like 0, 1, 0.3, 0.7. So the matrix P itself here has a 0 in it. But if we go back to the definition, all we need is for some power of P to have positive entries. So if P has a 0 in it, let's try calculating P squared and see if that 0 goes away. That's the idea. Let's see if we can make the 0 go away just by taking powers of P. So we're going to take 0, 1, 0.3, 0.7, and we're going to multiply it by itself using matrix multiplication. So we're going to circle the rows of our first matrix, columns of our second matrix, and let's see what we get here for P squared. So during our multiplication, we get 0.3, 0.7, 0.21, and 0.79. So we have created a situation where now every entry in that matrix is positive, or said differently, there are no zeros in that matrix. So again, the answer is yes. And let's see an example now in part C of what it looks like if the Markov chain is not regular. So let's start a fresh page here. We'll continue this question, the part C. Okay, here we go. So we're going to be given another matrix P, and this time it looks like 1, 0, 0.5, 0.5. So P right now has a 0 in it. Let's see if we square P, if that 0 goes away. If it does, then the answer will be yes. Okay, so we're going to multiply P by itself. Do our usual matrix multiplication. And what we're going to get, 1, 0, 0.75, and 0.25. Okay, so this matrix P, or this matrix P squared now, it's still got a 0 in it. So now we're going to check the next power of P. As soon as we create a power of P, whether it's P cubed, P to the 4th, P to the 5th, whatever the case may be, where there's no 0 in there, then we can say, yes, the Markov chain is regular. But as long as we keep getting zeros, we're going to have to keep investigating the next power of P. Okay, so let's think about P cubed here. We would take P squared, multiply that by P. Let's do that in the next line. So we figured out that our P squared, 1, 0, 0.75, 0.25, and we're going to multiply that by the original matrix P, 1, 0, 0.5, 0.5. Now again, we're going to get a 0 in the next step, and if we were to actually erase these numbers here, we can start to understand why. So I'm just going to write number, number, because it turns out that these specific numbers are not going to matter for the discussion. See, whatever these numbers are, we are still going to get a 0 when we do our multiplication. And the position where the 0 is going to come up is going to be in this top right corner here. So let's see what happens when we take the top row and do the dot product with the second column there. We are going to get 0. And that would be true even if we investigate the next power of P, the next power of P, P to the 4th. If you take P cubed times P, again, you're going to have this situation where when you multiply the top row with the second column, you are going to get a 0. in this position. That's just because we're seeing 1, 0 coming up always in the top row of these powers of p. So if you imagine that you've got 1, 0 over here in your p cubed, every power of p is going to have 1, 0 in that top row. And then we have 0 and some number here. Doesn't matter what that number is, we're going to create a 0 in that top right. So this is an example of a Markov chain that is not regular. And the good news is that in this section, we're going to focus on just the regular Markov chain. So I show you this part C just to show you what can go wrong. But we'll focus mostly on the types of Markov chains that we saw in part A and part B, because those ones have really nice properties. So now that we understand what a regular Markov chain is, we'll just restrict ourselves to those, and we're going to explore what we can do with these regular Markov chains. So let's start a new example here. We're going to make this more concrete. New page. New example. So let's go back to the clean hair shampoo situation. What we were doing there was looking at whether people who were buying shampoo were our customer or whether they were consuming another brand. And the transition matrix, the way we set that up, we use categories Y and N for yes and no. Yes meaning someone was our customer, and no meaning they were using another brand. So we had our Y and N like this. And our specific numbers in our transition matrix, 0.9, 0.1, 0.2, 0.8. So same numbers as we had in 7.1. So we're going to make two observations about this particular transition matrix. And notice that this is a regular Markov chain. All the entries in P are positive, so it's a regular Markov chain. These observations that we're going to make are actually going to apply to all regular Markov chains. So with this example, we're just going to play around with the numbers, make some observations, and then we'll write down some general facts after we've made those two observations. So first thing we're going to notice, let's say we take the matrix 0.667, 0.333. So this is a state matrix, and you can imagine this as encoding what percentage of people are buying our brand versus what percentage are not buying our brand today. So let's say right now, about 67% of people are buying the clean hair shampoo. That's massive. 33% buying some other brand. Okay, so we're going to multiply that by P. And let's just see what happens. So multiply that by 0.9, 0.1, 0.2, 0.8. So feel free to use your calculator for this. What happens is that what comes out is exactly the state that we started with. So what comes out of this? Let's write down our calculation here. So you can check, comes out to 0.667 and 0.333. So if you were saying this intuitively, you could say the next state equals or is the same as the previous state, or the current state, even we could say. Let's say that as the current state. So what's happening right now is the same as what's going to be happening on the next shampoo purchase. And that's really just a fluke of these numbers that we started with. It's the fluke of this 0.667 and 0.333, that when we take that as our current state and we do the transition, next state ends up being the same as the current state. Okay, so that's one observation. Second observation, related to this special state here where we have 67% and 33%. Let's say we start with any initial state that we want. Let's just say, for example, our initial state 0.4, 0.6. So 40% of people are buying our brand, 60% are buying the other brand. Let's just say that's what we started with. Let's say at the beginning of this year, for example. And then every month people are going out buying shampoo. So after the next purchase, we would have S1, which if we wanted to calculate that, we go S0 times P. If you wanted to calculate that, you could check. It comes out to 0.48, 0.52. And then if you were interested what's going to happen on the next purchase would calculate S2, S3, etc. And eventually, if you were really interested, you could go all the way 8 states into the future. If you were to do that, 0.651, 0.349, and of course, there's nothing special about 8, you could keep going. So you could go 100 states into the future, 1,000 states into the future, etc. So let's just think about what would happen as k goes to infinity. We're thinking about sk. So when you say k going to infinity, that's just roughly, very roughly speaking, like saying, let's just imagine k is some really big number. Let's think about what sk would look like. So S100 or S1000, for example, is going to be pretty close to 0.667, 0.333. So you might ask, where exactly did these numbers come from? Well, these are coming from the numbers that we saw in our first observation. See, these were the special numbers that if we put those into our state matrix and then do the transition, the next state is the same as the current state. So if you were to follow this process down, do S100, S1000, if you had the time to do that or you wanted to do that with software, you would find that those states would look like what we saw in the first observation. So that seems reasonable because with S8 we're saying, okay, we're already at 65%. Yes, seems reasonable that we would be able to get to, between 66, 67%. And that maybe at some point it could stabilize. So with that exploration out of the way, let's try to encode this with a definition and some more general facts so that we can see how to apply this to other Markov chains. So let's bring our page back here. New page. Here we go. And let's work on a definition. So let's say the state matrix S is called a stationary matrix. Stationary. Stationary matrix if SP equals S. So that was the same setup we had in observation 1. You put your state, you start with your state, you multiply by P to let it transition, and you come out with the same state that you started with. So the next state is the same as the current state. If that happens, then S is called a stationary matrix. Stationary meaning doesn't move or doesn't change. So when you apply P, it does not change. Okay, so here's our main fact around these regular Markov chains. Let's start off by saying let P be the transition matrix for a regular Markov chain. So that word regular is really important. Then we can conclude a couple of different things. And these two things will be tied to the two observations that we made in the previous example. So 1, there is a stationary matrix S. So stationary matrix, we're always going to use the symbol S for a stationary matrix. So we say this because if someone just gives you a Markov chain, it may not be entirely obvious that there even is a a stationary matrix. So this fact is telling us anytime you have a regular Markov chain, guaranteed, there is a stationary matrix S out there. And once you get into that state, or even near that state, you're going to stay very close to that state. Very close to that state for all future states. If you theoretically were ever able to reach that state, you would stay exactly in that state for all future states. In practice, once you get close to it, you're going to stay close to it. All right, so there is a stationary matrix S like that out there. And second property is that as k goes to infinity, Sk goes to S. All right, so that's just saying as you look far into the future, right, when k goes to infinity, just think big number like 100, 1,000, 10,000. When you look 100 states into the future, or 1,000 states into the future, 10,000 states into the future, you're getting something pretty close to S. What you can do, if you prefer, you can just say that's approximately equal to S. You can say Sk is approaching S, or you can say Sk is just pretty close to S. Either way. Either way is good intuitively. So what's important here is that we are working with a regular Markov chain. That's why we spent time at the beginning defining what a regular Markov chain was. So if you've got a situation where P has all positive entries, or if you have a situation where some power of P has all positive entries, then we're sure that we will reach this stationary matrix or get very close to it eventually. However, if someone gives you a Markov chain where P has a 0 in it, and as you keep taking powers of P, you keep having a 0 in it, then in that situation, you may bounce around between different states without ever reaching any kind of stability. So that's why we need to underline that word regular there. All right, so what we're going to do for the rest of this section, we're going to do 2 different examples, and the main thing we're going to practice is just finding the stationary state. And that's what allows us, the stationary matrix or the stationary state, and that's what allows us to do some long-term prediction. All right, so example, we're going to be given transition matrix P, and we're going to use 0.9, 0.1, 0.2, 0.8. So I'm just checking here. Those were the same numbers as we had for our clean hair shampoo. So we're building on that example, and what we're going to do is find the stationary matrix. So stationary matrix. In some courses, you might call this the stationary state, or sometimes called the equilibrium matrix, or equilibrium state, or steady state. Those are all different words for the same idea. It would be a topic that you'd be likely to see in economics, for example. So we're going to see if we can find that stationary matrix. All right, so first thing we should do here, let's introduce just some notation for the quantities that are going to be in S. So S is going to be a single row. It's going to have 2 numbers in it, and those numbers right now are unknown. So why don't we call those 2 numbers A and B? All right. Now, what we know about the stationary matrix, main property that we know, just by definition, coming back over here, we know that SP equals S. So once we get into this state, theoretically, if we were able to get into that state and then we do the transition by multiplying by P, we would get back that state again. Or in practice, once you get very close to that and you do your transition, you stay very close to that. Okay, so let's put in some numbers here. So here's our S. We're going to multiply by P, 0.9, 0.1, 0.2, 0.8. And we're saying once we do that multiplication, we are still going to have S coming out at the end. So let's actually perform the multiplication on the left side. Okay, if we do our multiplication, we get 0.9 times A plus 0.2 times B. So that number is the first number of the state matrix. And then doing the second column, first row with the second column, 0.1 A plus 0.8 B equals AB. Okay, now when we say that two matrices are equal, we're saying that the corresponding entries are equal. So we're really getting two different equations here. One equation is telling us that these two things are the same. So one equation is saying 0.9A plus 0.2B equals A. That's one piece of information about A and B. And the other piece of information is that the second two numbers also have to be the same. So 0.1A plus 0.8B equals B. So we've got two equations. I'm going to copy these onto a new screen, and we are going to go about solving a system to figure out what A and B are. Okay, so new screen. Let's do it. There we go. And I'm just going to recopy our equations. So at this point, we've got two equations. Actually, I won't call them 1 and 2 just yet. We'll see why in a second. So first equation was that 0.9A plus 0.2B equals A. And I'm just going to leave some room on the right here because we're actually going to simplify this equation. Second equation, 0.1A plus 0.8B equals B. And again, we're going to simplify that one as well. Okay, so that's exactly what we had written down on our previous screen, and we're going to go from there. So normally when we're solving systems of equations, we like to have all our variables over on the left side. So let's subtract A. We'd have 0.9A minus A plus 0.2B equals 0. So that way we've got all our variables over on the left side. And then you could collect these A's together. You could say, well, how many A's do we have? We have 0.9 minus one of them. So if you did 0.9 minus 1 on your calculator, that would be minus 0.1 is how many A's we've got. So minus 0.1A plus 0.2B equals 0. Okay, let's do the same thing for the second equation. We're going to bring all our variables over to the left side. So initially this would look like 0.1A plus 0.8B minus B equals 0. And then just collect the B terms. If we ask how many B's do we have, 0.8 minus 1 of them is minus 0.2 B. So our second equation looks like 0.1A minus 0.2B equals 0. So to summarize, we've got two equations so far, two unknowns. But what is unfortunate here is that it turns out that the second equation is actually a multiple of the first equation. You might notice that if you take equation 1, you multiply it by -1, you're going to get equation 2. So unfortunately, there's not enough info at this point to solve the system. The good news is that we do have another piece of information about A and B. So remember how we said that our state matrix, specifically the stationary matrix AB that we're looking for here, this is a state matrix, and in any state matrix, the entries are going to add up to 1. So the other information that we know is that A plus B has to equal 1. In other words, in general, when you're solving this type of problem, you're going to let SP equals S. That's going to give you two equations. Those two equations will give you incomplete information, and then you need to remember to add in a third equation, which is A plus B equal 1. All right, so now that we've got that, let's put it into an augmented matrix, and we will find our solution. So we're going to build a matrix that looks like this. Our variables are going to be A and B. We can choose which equation we want to write first. I would suggest we write the third one first, just because the numbers are nice there. That way we'll have a 1 in the upper left when we do our Gauss-Jordan process. So we'll have 1, 1, 1 across the top row, and then we can do the other two in either order. So if I want to do equation 1 minus 0.1 0.2, 0, and then we'll do equation 2 next. So 0.1 minus 0.2, 0. So there we go, and we're going to do our Gauss-Jordan and find A and B. So we've already got a 1 in the upper left. That's great. We are going to now get zeros in the rest of that first column. So we'll go row 2 plus 0.1, row 1, and row 3 minus 0.1, row 1. All right, so top row, 1, 1, 1. Second row, we're going to get some practice with our row operations here. We'll go row 2 plus 0.1, row 1, 0, 0.3, 0.1. And then row 3 minus 0.1, row 1, 0, 0.1. Oh, sorry, it's not 0.1. It's minus 0.2 minus 0.1 is minus 0.3, and then a minus 0.1. So there we are after cleaning up our first column. And now, this was our previous pivot. Now we're going to move down and to the right. Our next pivot is going to be in this position. So let's finish off the calculation over here. All right, so now we want to take row 2 and we want to divide it by 0.3 so that we're creating a 1 in this position here. And if we do that, we're going to need to figure out what 0.1 over 0.3 is. So if you've got decimals in your fraction like this, just consider multiplying by 10 on the top and the bottom, and then that gives us 1 over 3. Alternatively, you could use decimals and you could just say that's 0.33 if you wanted, but if we want an exact answer, it's 1/3. Top and bottom rows will not be changing here, so we'll recopy those, and then we got one more step to go, just to clean up that second column. This is going to be our final step here, so I'm going to write on the A and B so that we remember what we're solving for. And middle row looks great. This is our pivot. We're going to use that to clean up the second column here. And let's think about our row operations. So we'll need to go row 1 minus row 2, and we'll need to go row 3 plus 0.3 row 2. So let's try that. Row 1 minus row 2 is going to give us 1, 0, and then over here we'd have 1 minus 1/3. So that would be like 3/3 minus 1/3 is 2/3. Okay, and then bottom row, we're just going to get a nice row of zeros all the way across here. So 0, 0, and then you can check on your calculator if you go minus 0.1 plus 0.3 times 1/3. Try that on your calculator. That's going to give you 0. So zeros all the way across there. Great. So now we're in a position to just read off the solution. If we look at what the top row is saying, it's saying A equals 2/3. Second row is saying B equals 1/3. And bottom row, 0 equals 0, is giving us no info. That's because one of our equations just contained redundant information, contained information that was already encoded in another equation. So you're just going to always get a 0 row in a problem like this. So the answer then, remember we said our stationary matrix at the beginning of the problem, we were calling that AB, just to give names to those entries. And now we've figured out exactly what that looks like. So instead of saying AB, let's just put our numbers in here. So 2/3 and 1/3. So that's our stationary matrix. That tells us that as we look long term in this clean hair shampoo company example, what percentage of the market share is clean hair going to have? Remember our categories were yes and no in that order. So they are going to have 67% of the customers, 2/3 of the customers long term, and long term 1/3 of all shampoo customers will be with other brands. Wow, so clean hair is really going to dominate this market in the long term. And as we look into the future, 8 states into the future, 10 states into the future, we're going to be getting closer and closer to this stationary matrix. So to finish off this example, or this section rather, we're going to do one more example of finding the stationary matrix. It is a process that, requires a little bit of practice. So I think after we do a second example, should become more clear. Let's try that. So here we go, new problem. P is equal to 0, 1, 0, 0, 0, 1, 0.9, 0.1, and 0. So part A, we're going to find the stationary matrix. And then part B, we'll just do a bit of an interpretation after that to make sure we understood what we've done. So the stationary matrix in symbols, we call it S. And if we're talking about a situation where P is 3 by 3, then we actually need 3 entries in this matrix. So let's just call them A, B, C. You can call them whatever you want. And what we know about the stationary matrix is that SP equals S. So that means if we take A, B, C, and we multiply it by our transition matrix, let's write that out, then we are going to get that same stationary matrix back again. So the stationary matrix is very special because once you get into that state and you do your transition, you're going to be in that state again for the next state and all future states. All right, so let's multiply out on the left side what we've actually got. So circle rows of the first matrix, any columns for the second matrix, and we'll just multiply this stuff out. So it's going to be 0.9c is the first number. Second number is going to be A plus 0.1c. So I'm just spacing out the entries so that it's easier to read. And then the third entry is going to be B. Okay, so that's what we've got there. And we're saying that's equal to A, B, C. So let's think what we did in the previous example. We said once you have a matrix equation like this, you're really getting several pieces of information for the price of one. So one piece of information is that the first entries must be equal. 0.9c has to equal A. The middle entries must be equal. A plus 0.1c is the same thing as B. And then third piece of information, the last entries have to be equal. So B equals C. But this is sort of a strange way of writing the system. The standard way of writing equations and of writing systems of equations is to have all your variables on the left side. So it'd be better if we simplified each of these equations and we said things like minus A plus 0.9c equals 0. Things like A minus B plus 0.1c equals 0. So you're going to have 0 on the right side because you brought all your terms over to the left, and we're just bringing terms over with a sign change. We always write the terms in the order A, B, C, so it's good to write them in that order so that when we're filling in the matrix, we fill it in properly. So the last equation would become B minus C equals 0. So you could call these equations 1, 2, and 3. And just like in the previous problem, this system never encodes all the information. So there's not quite enough information at this point. We always, at the end, also have to introduce a last equation. In this case, it would be equation 4. And the last equation is that all these numbers have to add up to 1. That's always true for any state matrix. So all the numbers here have to add up to 1 because these numbers are just encoding different probabilities, and together they cover all possible situations. We don't know in this situation what the states are or exactly what process the Markov chain is describing, but what we do know for sure is that these are probabilities and they add up to 1. Okay, so now we're going to build our matrix. We've got 3 variables, A, B, and C, and we're going to have 4 equations. So the last equation is always the best one to write first because it's got the nicest coefficients in it. So we're just going to have 1s all the way across. And then the other ones you can write in any order, probably just the order in which you wrote them down. So -1, 0, and 0.9, 0. So that's equation 1. We had equation 4 at the top, and then we'll just fill everything in for equations 2 and 3, like that. So 1 minus 1, 0.1, 0, and 0, 1, minus 1, 0. So let's just take a second, make sure that we've copied that properly. That looks good to me. And then we're going to do some Gauss-Jordan here. So if you put the last equation in first, then you'll always have created a situation where you've got your 1 in the upper left. So that's great. Let's go row 2 plus row 1, and also row 3 minus row 1. And that's going to clean up the first column for us. Okay, so top row stays the same. Row 2 plus row 1, 0, 1, 1.9, and 1. Row 3 minus row 1, 0, minus 2. We're going to have 0.1 minus 1 is going to be negative 0.9, and then negative 1. Okay, and then bottom row does not need to change because we've already got a 0 in that position. Okay, so we've got a little bit more work to do. I think just for the sake of space, we should start on a new screen, and then we'll be able to finish from there. So let's just copy this matrix over. I'll write it up quickly again, and then we can start where we've got a bit more room. Okay, so top row, we had our 1s all the way across. We had 0, 1, 1.9, 1. 0, minus 2, minus 0.9, and negative 1. And then we had 0, 1, negative 1, 0. So that's where we were at just from our previous screen. And then we can finish up from there. Great, so here was our pivot from our previous step. Now we're going to move down and to the right. This guy's going to be our pivot for the next step. Very nice that that's already a 1. So we're just going to focus on getting zeros in the rest of column 2 then. So row 1 minus row 2. Row 2 is our pivot row in this context. So we'll go row 1 minus row 2. We'll go row 3 plus 2 row 2. And also row 4 minus row 2. So lots of extra practice with our row operations to help us get more comfortable with Gauss-Jordan. All right, row 1 minus row 2 is going to be 1, 0, minus 0.9, and 0. Second row is perfect as is, so let's not worry about that. Row 3 plus 2 row 2, 0, 0. You can try this on your calculator. We're going to go minus 0.9 plus 2 is going to be 1.1. And then minus 1 plus 2 is going to be 1. Okay, there we go. And then row 4 minus row 2, 0, 0, minus 2.9, and minus 1. So that's where we're at after having cleaned up the second column. And from that point, we are getting close to a solution now. Just looking over my work, I noticed there's something, a little adjustment we need to make here. I think with this one, maybe you noticed that something was a little off there. Let's figure that out. Okay, so let's look at the right rows here. We're going to go row 3 plus 2 row 2. Minus 0.9, actually write down what we're doing, minus 0.9 plus 2 times row 2, so it's supposed to be plus 2 times 1.9 there. Okay, that looks a little bit better. It's going to be 2.9. So sorry if that caused confusion. Great. So now, totally happy with that. First 2 columns have been cleaned up. and we're going to now fix up the third column, third and last column. So just 2 more matrix steps to go. So from our previous pivot, we're going to move down and to the right. Now this 2.9 here that we've just figured out, that's going to be our pivot for the next step. So let's do that over here. We're going to take row 3 and we're going to divide by 2.9. That's going to give us 0, 0, 1. And then on the right side, so let's just do a vertical bar there. On the right side, we need to think about what's going to happen when we go 1 over 2.9. Well, in this situation, usually good just to multiply top and bottom by 10 to clear the decimal. And then you multiply numerators together, multiply denominators together. So 10 over 29 would be the best way to say that, or you could turn that into a decimal. All right, so we're going to recopy our other 3 rows. Just make sure everything's being copied correctly here. That looks good. And then for the bottom row, 0, 0, minus 2.9, and then a negative 1. Great, so there's our pivot. Pivot row is row 3, and we are going to just finish this off. So we're going to go things like row 1 plus 0.9, row 3, row 2 minus 1.9, row 3, and then row 4 plus 2.9, row 3, and that's going to finish it all up. All right, so let's start on the top row. Row 1 plus 0.9, row 3 is going to be 1, 0, 0. And then over on the right side, we'll have to do 0 plus 0.9 times 10 over 29. Okay, so easiest way to figure this out, the decimal or any number multiplied by a fraction is just going to multiply with the numerator. So you go 0.9 times 10 gives you 9, and denominator stays the same. So 9 over 29 would be how you would give it as an exact value. Okay, row 2 minus 1.9, row 3, 0, 1, 0, and then a little bit more fun with fractions. So 1 minus 1.9 times 10 over 29. Just do that calculation underneath. Let's figure out how many 29ths we have. So 29 over 29 minus, now the number in front of the fraction just multiplies with the numerator. So minus 19 over 29. You could say that's 10 over 29, or just go with a decimal if you prefer. So that's how we got that number. Third row not changing, so 0, 0, 1, 10 over 29. And then I'll just add a little bit more room to do our bottom row. So fastest way to figure out the bottom row, just from a conceptual point of view, we know that there was not enough information in the system originally to solve the system. What that tells us is that there's going to be a 0 row at the bottom. So without even really thinking about it, you could say that conceptually without calculating it. But if you do want to check that, that would be great. That would confirm we're on the right track. So row 4 plus 2.9, row 3, we're going to have, sure enough, zeros all along the left side. And then if we go 0.1, or sorry, it's negative 1 plus 2.9 times 10 over 29. Yep, sure enough, that does give us 0. So you can try that on your calculator. Right, so the names of the variables here were A, B, and C, and we're now ready to write down our answer. So top row says A equals 9 over 29, middle row says B equals 10 over 29, and third row says that C equals 10 over 29. So C is equal to B. Bottom row gives no information, so we can ignore that. So to answer the question, here's our stationary matrix. 9 over 29, 10 over 29, 10 over 29. And if you wanted to turn these into decimals, that's fine. I figure I'll just show it to you the hard way. I'll give you the exact values. And then if you want to make it a little easier on yourself and do it with decimals, that's okay. So quick follow-up question. I'll just do this right at the bottom here. As k goes to infinity, what does SK look like? So we're asking, if you look 100 states into the future, or 1,000,000 states into the future, or even 50 states into the future, what are these states, S100 or S50, going to look like? Well, the answer is they're going to look pretty much like S. So you can say approximately S. The further you go into the future, the closer and closer you're going to get to S. And each state that's close to S, as you transition, you multiply by P, you're going to get another state that's even closer to S. Theoretically, yeah, you could end up exactly in state S, and then from there, every transition is just going to give you exactly the same state again. So that's the end of our discussion on Markov chains. Essentially, we've figured out how to build transition matrices. We've figured out how to encode states in a matrix. We've figured out how to look a few states into the future. That was all in 7.1. And then now in 7.2, we've seen the beauty of regular Markov chains where we can do long-term prediction. And we figured out how to find this stationary matrix, or sometimes called the steady state matrix or equilibrium. That's really useful for prediction in the real world. So thanks for watching.